Welcome for today's QuTech360 seminar. Today's presenter is Xin Zhang. Xin Zhang is a postdoc researcher in the group of Vandersypen here at QuTech. And as usual, I give a little bit of a background of the speaker. So Xin received his PhD in physics at the University of Science and Technology of China in Hefei in 2021. And there he worked already on some related topics. He worked on measuring electron spin relaxation rates and spin valley mixing in silicon quantum dots. But now he switched also the material and currently is investigating spin control and analog quantum computing in a 2x4 quantum dot germanium quantum dot array, a ladder, here at QuTech. And before I give him the stage, I also want to make a quick announcement. The next QuTech360 seminar will be in September. There will be no seminar in August. And with this, please.
Thank you, Max. Thanks for your introduction. And welcome, everyone. Today, I'm Xin Zhang at the introduction. And today I'm talking about universal control and benchmarking of 4 singlet-triplet qubits in germanium quantum dots. So this is we have already have the paper on the archive that if you are interested, you can have a look. So talking about the qubits, I think you are familiar with the qubits here. And this is the picture that's showing we have different types of qubits on different physical platforms, like photons, cold atoms, and similar qubits or topological qubits, and trapped ions. The picture I like most of here is that they put a spin in the stage center. So maybe a spin qubit is the future. And here in quantum dots, we put a spin into a quantum well. So this is the example of the germanium quantum well sandwiched with 2 silicon germanium alloy. And in this quantum well, the charges on the valence band, they are confined in the z directions. So we are controlling the holes rather than electrons in this heterostructure. And if we have a 2-dimensional electro gates on the top of the device, on the top of the heterostructure, we can form a 3-dimensional control of the charges. And this comes to the into play of the quantum dots. This is a 0-dimensional identity. And we can trap the charges and control the spin. And to demonstrate the spin control, there are several different ways of the spin encodings in semiconductor quantum dots. That you can encode spin qubits in various different ways. The first straightforward way is the single spin qubits. I think everyone is familiar that you just encode the qubit into spin up and spin down. And this type of qubits can have a very high single and 2 qubit gate fidelity. And also it's very efficient encoding because you only need 1 dot for 1 qubit. But the drawback of this type of qubit is that you need a macromagnet or other additional ingredients like antenna or the natural spin of the carbon in the system to introduce a spin control. And also the result is very complicated if you consider that you have to use an ancilla spin for polyspin blockade or use a reservoir for result because we don't have a direct spin measurement in the quantum dots. We have to use a spin to charge conversion. And also for if you use microwave to control the spins, due to the quantum dot the size is very small, you are easily to dissipate heat to other quantum dots and you have a microwave crosstalk. So the people have another idea that maybe we can encode the qubits into 2 spins. The 2 spin qubits have a good advantage that they have a natural spin readout basis. So they don't need any ancilla. They just use the polyspin blockade themselves. So the polyspin blockade means that if you move 2 electrons to 1 quantum dot, if they are single, they can be moved to the 1 quantum dot. But if they are triplet, they cannot be moved. And this is a straightforward way for the singlet-triplet qubits. And also, you don't need to use microwave for the qubit control. You can just use the baseband control because you can control the charge occupation of the quantum dots, and also you can control the spin states. But still, you need a micromagnet or semi-orbital coupling to have a universal control of the such qubits. And another disadvantage of this type of qubits is that two-qubit gate is very complex because you have more states in the space, in the qubit space. For example, if you consider two ST qubits, then you have like 16 states to consider, and then you are easily getting into leakage to other states. And the third type of qubit is the qubit that you use 3 quantum dots. So we call it the exchange-only qubits because you only use the exchange interaction in the quantum dots. You don't need any micromagnet or spin-orbital coupling in the system. In this way, you have full electrical tunability because you can just tune the exchange coupling of the left double dot pair or the right double dot pair. The drawback of this type of qubits is that you have full electrical tunability, and then you have to control it using all the baseband process, and it can be very complicated with 3 spins and a very large qubit space. And also, you are easily getting into leakage. So to do a summary here, that if you go from 1 dot to 2 dots and to 3 dots, you get rid of the control requirement or read requirement in the system because you have more electric control in the system. But the drawback is that you have more control capacity because you have leakage, you have more, you need to use more control process. So actually, this is a double-edged sword. So how can we solve this? A naive idea is that if you just choose singlet-triplet qubits, it's in between, so they have a balance between 2 things. I don't know if I can convince you, but let's focus ST qubits from now on. And this is the history map of the ST qubits throughout the years, in the last 20 years. So the single qubit fidelity has been up to the 99%, both in the gallium arsenide quantum dots and the silicon germanium quantum dots. And here they use a pulse optimization to make the fidelity very high. And for the 2 qubit gate fidelity in gallium arsenide quantum dots, they have achieved the 90% gate fidelity and the 93% Bell state fidelity. It's good. And for the number of qubits, the maximum number is 4 in a 2x4 array in gallium arsenide quantum dots. But the pity is that they have never reported any numbers of the single or 2 qubit gate fidelity. So you may ask, what's the next step? Can we combine all the attributes into the same device? I would say yes. That's why I'm here today. And this is a device, a 2x4 germanium quantum dot devices fabricated by Stefan Usselholt with the help from Manuel Vander's group. And also the germanium quantum well is fabricated by Amir Samak and the Scarpucci group. So now I just want to say more things about the electrical gates we used in the device. So we have a 4-layer gates here to have a good control of the quantum dots. And the first layer is the omics. They are purely metals to acting as a reservoir for charges. And then we have a screen gate. This is a second layer to confine the path for the charges move. And then the third layer is the plunger gates. They can define the quantum dot positions. So this is a 2x4 array with 4 sensors on the corners to act as the sensors. And then the finally is the barrier gates that we can control the tunnel coupling between 2 quantum dots and the tunnel coupling between quantum dot and the sensor. So for the first thing we want to characterize for this device is to measure the charge states in the quantum dots. And here in this device, we use the bottom 2 sensors to sense the whole array. And this is the result by changing the gate voltages. And we can form 4 double quantum dots pairs along the runs of the ladder. So you can see we can empty totally the quantum dots to 0, 0. And we can also confine them into 1 electron per dot. Actually, here there's a hole because it is germanium. And if you look at have a diagonal line cut here in the one-way regime, actually you can move in the electrons into different quantum dots by playing with the plunger gate voltages. So here we have an illustration that you can control the difference between the gate voltages. We call it the detuning, changing the charge state from two holes in one quantum dot to one hole per quantum dot, or two holes in the other quantum dots. In this way, you can change the charge state in the double quantum dots. And accordingly, you are changing the energy levels in this system. So for two spins, you have one singlet and three triplet. And if you control the detuning between the quantum dots, you can control the charge state and then control the energy levels of singlet and T minus states. And you can see anti-crossing between S and T minus because of the spin orbital coupling in the germanium quantum well. And not only you can control the charge state by the detuning, you can also control the spin states by the barrel gate voltages. So the barrel gate voltage will directly control the exchange coupling between two spins. And here is that if you increase the exchange coupling in the double quantum dot, you will change the anti-crossings numbers between S and T minus. So here I can walk you through this diagrams. So here, if you can imagine that the exchange coupling at the detuning center, if they are smaller than the Z energy, the T minus states will be the ground states. However, at 20 or 02 states, the singlet is always the ground state because the two charges are in the same quantum dots. So in this way, you have a two anti-crossing between the S and T minus. However, when the exchange coupling is similar to the Z energy at the center, then you only have one anti-crossing. And then if the exchange coupling is much larger than the Z energy all the way to detuning, you're always in the ground state of singlet. So you don't have any anti-crossing anymore. And in the experiment, we can prepare two charges in the singlet states and then move the detuning to cross these anti-crossings. If we can spend a fixed time there, and if we got a triplet, we can go back to the 20 state to measure the if it is a singlet or triplet. So this is an experimental result that we can see that when the barrel gate is very high, the exchange coupling is very small. We have two anti-crossings in the detuning positions. And then if you increase the exchange coupling, you have one position of the ST minus anti-crossing. And then if you increase the exchange coupling more, then there is no anti-crossings anymore. We can perform the same experiment on the four double dot pairs and see the same physics. It means that the dot pairs are homogeneous and we can control using the same physical mechanisms. And now if you focus on the single spectrum like this, if we just on purpose tune the exchange coupling to be equal to the Z energy at the center of the detuning, and here the Z energy is equal to the exchange coupling. So similar Z term in the Hamiltonian of ST minus states, they are zero. And then the similar X term from the spin orbital coupling can drive the qubits rotating from S and T minus. This is X rotation actually. And this is the process we use. So we drive the qubits from 0 to 0 state, initialize as a singlet, and then drive it past through the detuning anti-crossing, and then spend some time there and go back for the readouts. And the barrel gate is to use to tune the position to make the exchange coupling equal to the Z energy at the center detuning. The result is like this. So now what we can say, we are going from 4 double dot pairs to 4 qubits because we can achieve X rotations for all the qubits. And this is the figures as a function of the barrel gate voltage. And it is like a chevron patterns, like a Rabi oscillations. And at the central part, you are doing exactly X gate. And the X gate oscillation speed is around 5 to 10 megas. I would say they are similar to the result of single spin qubits. And you may ask that it is not a qubits because you don't have a universal control, you're using only X gate. So now we are considering if we can do more control of the qubits. What we can use is the similar Z term in this Hamiltonian. If you increase the similar Z term by increase the exchange coupling, if they are the two terms if they are equal, you are rotating the qubits along axis that has an angle of 45 degrees with respect to the x-axis and the z-axis. And if you rotate qubits by doing a pi rotation, this gives you a Hadamard gate, actually. And we do even a step further. So if you first do a Hadamard gate and then do an x rotation of 180 degree, you are in the end get a y rotation. This is a half pi. This is a half pi rotation. And this is the experimental process. So we still drive the qubits initializing from singlet and drive the qubits to the center of 1,1. The thing is that if you look at the blue double arrow, this is the x rotation we have calibrated before. And now what we need to calibrate is the Hadamard gate in this sequence, and the waiting time and also the barrier gate voltage. We repeat the same sequence twice to have a maximal visibility between singlet and triplet. And this is the experimental result of such calibration. So if you look at the inside is the simulation result. And when the similar Z term and the similar term, if they are equal, and at some point you are going to the square root of y gate. And we have a similar result of the experimental things, and we can calibrate the square root of y gate at the fixed TV time and the fixed barrier gate voltage. And we do the same thing for all the 4 qubits together to calibrate where the position of the square root of y gate in the system. So in this way, we can say we have x rotation and y rotation for the universal control of the qubits. And this is the first demonstration, examination of the gate fidelity. So we use a randomized benchmarking. There's a sequence of Clifford gates. The Clifford gates can be decomposed into different gates like X gate, Y gate, and identity gate. That's what we have in the instrument box. And after that, we can use a final Clifford gate that rotate the qubits to the singlet in the end. And we can measure the singlet probabilities of the qubits. And the singlet probability will decay as a function of the Clifford gates you apply. And by fitting this decay, you can get the fidelities of the single qubits. This is the average gate fidelity, and they are all over 99%. Apart from the randomized benchmarking, we also do the gate set tomography to characterize a single qubit gate. So the difference between the RB and the GST is that here we not only have terms that can amplify the noise, we can also have fiducial gates. And this helps us to recover the process matrix of the qubit gates. And then we can get a separate individual gate fidelity of the X gate and Y gate for the different qubits. Okay, now we can have a short summary that we have put ourselves into the same map and with 4 qubits together and with a single qubit fidelity of over 99%. And there's a missing blank here that we need to fill about the 2 qubit gate. And if you have any question, you can directly ask. And now I'm moving to the 2 qubit gate in the singlet-triplet qubits. So assuming that you have a single qubit energies like this, and you have 2 copies of it, and the 2 qubits is interacted with one another due to the exchange interaction between them. And then if you align one of the qubits that align on the shoulder of the detuning with a very strong qubit splittings, and then you scan the detuning of the other qubits. And if you will find, maybe you can find that there are 2 places that the two qubit energies can be resonant. And this resonating qubit energies will give you a swap interaction enabled by the exchange coupling in the system. And this is a process we used in the experiment. We first initialize all 2 qubits into singlet, and then rotate one of them into a triplet, and then we put them into this setup to find the position of the swap by scanner detuning and the waiting time here. And then we go to the polyspin blockade to read out the qubit state. This is an example of the swap result that we scan. You will find that there is a bigger set of oscillations in Q4. This is due to that you have a spiral coupling in the middle and you have a single qubit rotations. And what we are looking for is actually on the both shoulders of the detuning. The left one, you don't see oscillations because the exchange coupling is small because it is dependent on the detuning of the other qubits. So it is small here and you don't see any oscillations. And it is large enough on the right side that you can observe oscillations. So we can cleverly choose the position where we can observe the swaps. This is the result for the swaps for the Q1, Q2, Q2, Q3, and Q3, Q4. And it means that we can achieve the swap gates for all the neighboring pairs in the array. And the oscillation speed is over 10 megas. So we are confident that the chord is fine. Now we go to examine the swap we have in the device. The first thing is that the question is that if we can generate the entanglement using the swap gate. It is only universal when you have a two-qubit gate that can generate entanglement. So here we use a simple circuit. We have an acceleration of Q1 and then a halfway swap between the Q1 and Q2. We call it the square root of swap. And this can give us a Bell state, a generalized Bell state, because we have a phase here. And how can we prove that we generate such a Bell state? Is that we can recover the density matrix of the states. So our strategy is to use the quantum state tomography. We just do, after this circuit, we can do just a combination of single qubit gates that can rotate different parts of the information onto the z-axis. And then we can do the measurement experiment. So the first one is the readout matrix. Because here, if you want to just use the measurement probabilities, they can have errors because of the readout. And what you can do is that to initialize different states in the system and measure the readout result. And using this matrix, you can convert what you measure to the real probabilities in the system. What you think is real, there can be errors. And then you can convert back to the density matrix. And here we use another way that we call it maximal likelihood method that they can feed the result to a more physical density matrix. And we can believe the result is better by using this method. And after that, we can get the Bell state fidelity for all the qubit pairs. So they range from 70% to even 90%. And the concurrence can be as high as 65%. The concurrence is a measure of the entanglement. So if it is 0, it means that there is no entanglement. And if it is 1, it means that it is maximal entanglement. So the non-zero entanglement here, it means that we can surely generate entanglement using the swap gate we have. With all the swap gates, what we can do is we can do some quantum algorithm. So here we choose the algorithm that we want to do is to generate a remote entanglement using all the swap gates we have. So the idea is that we can initialize qubits into one qubit and 3 signals in the array. And then we can do the swap gate between Q1 and Q2. And after that, we can transfer the information from Q2 to Q4 by 2 swap gates. And if you can generate entanglement between Q1 and Q2, and after the state transfer, you can generate entanglement between Q1 and Q4. We can check the Q4 information by doing single qubit rotations. And the right is the figures. The left one is an experimental result, and the red one is a simulation result. So the check how do we can understand the checkboard pattern? Is that so you can imagine if you have no time in the swap interaction, you have a purely triplet in Q2, and then you transfer Q2 to Q4, and the Q4 will start execute rotations with a very high triplet probability. And if you have a full pi rotation of the swap, Q2 will be in the singlet state. And then you transfer Q2 to Q4, it will result in oscillation starting with a singlet. And if you have halfway of the swap, then you have a maximal entanglement between Q1 and Q2. If you only transfer Q2, this will give you just a mixing state. And the mixing state can never oscillate if you just control it. We can have 3 line cuts here. So you can easily see the out-of-phase oscillations between the upper one and the lower one. And in the middle, you have nearly no oscillations because you have a maximal entanglement between Q1 and Q4. And this is only a qualitative understanding of the remote entanglement. Actually, we have another way to prove the entanglement by a quantitatively measurement. It's a quantum state tomography. So we perform a similar circuit like before, and then we do single qubit rotations for Q1, Q4, and then do the probability measurements. This can give us the fidelity of 75%, Bell state fidelity, and the concurrence of like 22%. This fidelity is lower than the result of the Bell state between Q1 and Q2. And we can understand it because we can have errors in the swap gates, so that the fidelity is lower. So now we have filled the Fano blank in here. We have a 90% Bell state fidelity and a 75% remote Bell state fidelity. And but another number is missing is that the gate fidelity. So now we are coming to the final part of this talk, and that we are exploring the ways to try to check the 2-qubit gate fidelity. So for checking the 2-qubit gate fidelity, what we want to do is gate side tomography. But it turns out that we need circuit completion in this circuit. And that is to say that, for example, if you imagine you are doing a set of 2-qubit gates, you have single qubit and also 2-qubit gate in between. And if you want to do X rotation of Q1, you not only care about Q1, but also you care about Q2, because you need not only X rotation for Q1, but also identity gate for Q2. And if you look at our Hamiltonian, we have a problem that the qubit is never sitting there doing nothing. They are always rotating. And you have to cleverly choose a position that it do an identity gate. So our strategy is that you can change the Hamiltonian parameters in the way that during the fixed time of the X rotation of Q1, and Q2 is doing a 2-pi rotation. So this is an identity gate. And so now I will introduce the calibration we do. So this is a calibration process. So we perform a Ramsey sequence for Q2. We do X rotation 90 degree to the equator, and then we do an identity gate, what we think, and then we do X rotation back. So if the identity gate is perfect, you are initializing from a singlet, and then do 2 consecutive 90 degree rotations, you are fully in the triplet states during the time of the given by the X rotation of Q1. And this is the experimental result. So we fix the duration and we scan the barrel-gate voltage of the Q2. And we can find that at some point, the singlet is going to the full triplet state. And we choose a point here to do the identity gate. We choose a positive one because at the positive position, the channel is lower. And we can perform the similar experiment for all the single qubit gate rotations in the 2-qubit space. So like the identity gate for Q1 with X rotation for Q2 or Y rotation for Q2. And the same for the Q2, X rotation of Q1 and then the identity gate of Q2 and so on. And you can see here the orange circle means the position we choose for the identity gate of the one we don't want to like it not evolve. And this is the experimental result we get from the GST. So that you can see the fidelity is ranging from 87% to 97%. Admittedly, they are lower than the single qubit gate fidelity we measured before. That's reasonable because here we also suffer from the calibration errors in the identity gate and also the dephasing in the identity gate. And then in the same way, we also get the 2-qubit gate fidelity using the GST. So the right one is the process matrix of the square root of swap. And the left one is we have a theoretical model, and we can fit it using our theoretical model, and we can get the fidelity around 80%. This number is lower than the Bell state fidelity, because in the Bell state fidelity, we don't have an added gate. And also the gate processes are slightly different. And also Bell state fidelity is not a gate fidelity, it's just have a certain initial state, and the gate fidelity have a different initial state. So the fidelity of a real gate is lower than the Bell state fidelity. So now we can have a summary that we have put ourselves in the map. We can have a good single qubit gate fidelity and a 2-qubit gate fidelity. And also we have a maximum number of qubits equal to 4. And we do, to summarize, we even go a step further. So the first thing is that we first report a remote entanglement in an array, because we can control the whole array. And we have a 75% of the Bell state fidelity and 22% concurrence. And then we also explore the quantum circuit compilation that we can, the way we chose give us like a 87 to 97% single qubit gate fidelity. And we think in the future, we still have the challenges to improve. The first thing is the 2-qubit gate fidelity. So not only you can do a swap gate, but you can also do a CZ gate. And you can also do symmetrical control. Rather than control the detuning of the qubits, you can control the barrel gates. And that can maybe give you a better fidelity. And also for the quantum circuit compilation, that the strategy we use maybe is not optimal. We can choose other ways to compile the single qubit gates. And maybe other ways can give us a better fidelities. And we can also use a simultaneous qubit control or pause optimization. And finally, thank you for being here. And this work is in collaboration with Elizaveta Morozova. And also we get the theoretical support from Maximilian Rimba-Ross. And this work can never be done without the help from my colleagues from Vandersypen group, and also from Vanderhaus group and the Scabischi lab. Thank you.
Identify the leakage during the operation, especially for the 2-qubit gate? And is there a way to manipulate the qubit to reduce this leakage similar to exchange on the qubit?
And so for the leakage of the 2-qubit gate, Max has done a theoretical analysis, I think here. So the thing is that we put a single qubit in a very large qubit energies. So the large single qubit energies will surprise your leakage to other states. So actually, the leakage to the other states can be negligible in our case, in the 2-qubit swap. Yeah.
What are the most limiting factors for your fidelities?
I think for now, the fidelity is limited by the low frequency noise. I don't know what the origin of the low frequency noise. It might from a hyperfine interaction of our charge noise, because we see the parameters is always is unstable from measurement to measurement if you check it. Yeah.
Do you think that this is really the limiting factor, or the tuning of the device, for example, or let's say at the moment, like maybe like all the G factors and all the dots are completely random, you kind of really control them, or is this, or I mean, are these also limiting factors?
You mean when you consider scaling up the array?
Yeah, just mean if you could choose whatever you want for these parameters for your system, if you could, then would you get better fidelities than now?
I think now is fine. We are not limited by the inhomogeneity in the device. We just accidentally found that the G factor is homogeneous from 0.3 to 0.35, something like this. So this is good for us. We need to like check a larger array to see if it is inhomogeneous. Yeah.
So you did GST on your spin qubits.
Yeah.
Did you also were you also able to see the error generators of your gates?
Yes.
And then
Yes.
from the error generators, what does it say that is limiting your gate fidelities?
Yes, from the error generators, we found that the calibration error is very large, actually, because I think because of the calibration of the Y gate in our case is not we didn't optimize it. I think that's the main error.
So add to that, so like just number-wise, is the coherent error larger, or even if you consider how it goes into the average gate fidelity, is it still the limiting factor?
There's a square, if you look at it,
Yeah.
if you go into it after a very good calibration, it is smaller, and we are limited by the decoherence.
So after bit calibration, you get limited by decoherence.
Yes, yeah.
You said you had some problem with low frequency noise. Does it make it hard to use phase technology because of reality?
Yes, when we look at if the model valuation in the GST, we found the model valuation can be large. For single qubit case, fine to do the sequence to do 8 L equal to 8. But if we do it more, then we found larger model valuation. So that's why the GST result, the fidelity is lower than the RB result. Because I think we think RB don't have such a problem. Yes.
Thank you for the talk. About the entanglement, I have a couple of questions. First, to generate remote entanglement, did you ever consider like standard entanglement swapping or things like that?
You mean
generate the entanglement between qubit 1 and 2, 3 and 4, and then measure 2 and 3?
We haven't considered it. I think it is also depends on the swap gate fidelity. Here we choose to start with Q1, Q2 is because the Q1, Q2 has the best number, the best two qubit gate fidelity. And then if we transfer Q2 to Q4, the swap errors we don't care too much.
Yeah, sure. Error is going to be worse, but I'm wondering how much. And the other thing is if it's possible to do some entanglement distillation here.
I think the fidelity is still not that high. Like if you look at the concurrence, it's only like 60%. It's doable, but not high enough, I think. It's the swap gate is still limited by the decoherence because we align the detunings and they are very sensitive to the charge noise.
Perspective question. So what's next in this kind of line of thought with singlet-triplet qubits? Like you've done 4 and you're entangling them.
Yeah.
What's next for the other kind of qubit? What for this path?
I think for this path, if you really want to use the singlet-triplet qubits, what you need to solve is the 2 qubit gate fidelity. The 2 qubit gate fidelity is still low. And not only in our result, but in the result before. It is not 99%. So I think we need to solve this for the ST qubits. And I think it's doable because we haven't optimized the process and we haven't done exploration of the CZ gate.
Any more questions? If not, then I will close the session. And let's thank the speaker again.